Thanks a lot for inviting me. I'm very happy to be able to speak here. And yeah, so my title of my talk is Mustafin, Degenerations between Applied and Arithmetic Geometry. And the things I'm going to talk about are going to be partially based on joint work with Bing-Ling Li and Annette Werner, but it's also going to be very general, but also very vague, I should warn you, at least in parts. Okay, so what is the talk today about? The main players are degenerations. Degenerations are a central technique in the study of algebraic varieties. So the study of zero sets of polynomials in the easiest sense. And here on the right-hand side, we have a schematic picture of a degeneration that we will understand in maybe 5 minutes. And these Mustafin degenerations that give us the name for this talk, they are very special, but also very interesting class of degenerations. And they are distinguished by two special properties. The first property is that they may be computed in computer algebra systems. So you can actually choose global coordinates on these Mustafin degenerations and teach the computer how to compute them. And the second interesting feature that distinguishes Mustafin degenerations is that they have a very nice and very rich combinatorial structure. And we will see this later on in this talk. And due to these two features, they have applications in several different areas of algebraic and arithmetic geometry. So here we have a highly non-complete list. As also, if you can't associate anything with the words I'm saying on the slide, it doesn't matter for the rest of the talk. I just wanted to illustrate the vast array of applications of Mustafin degenerations. In 1976, they were introduced by Ghali Mustafin in his work where he generalized Mumford's seminal work on the uniformization of curves to higher dimension. In 2001, Gerd Faltings used them in the context of studying local models of Shimura varieties. In 2005, in the work of Kehl and Tevelev, Mustafin degenerations found an application in the context of Chow quotients of Grassmannians. And in 2011, Cartwright, Helbig, Sturmfeld, and Werner developed a combinatorial interface between tropical geometry and Mustafin degeneration. So tropical geometry, so much I want to say, will frequently occur as a verbal footnote in some sense in the rest of this talk. I don't really want to say what it is, but you can think about it as some sense of combinatorial shadow of algebraic geometry. So it's a combinatorial framework to study objects in algebraic geometry. And in 2019, building on work of Bing-Ling Li and myself that we will see later on, he and Zhang developed an application of Mustafin degenerations in perimeter theory. So as you can see from this slide, Mustafin degenerations have a very vast array and very diverse array of applications in algebraic and arithmetic geometry. So the talk today, I'm going to review some of the theories surrounding Mustafin degenerations. I'm going to give some classification results that exist in the literature, give an application in arithmetic geometry, more precisely in p-adic non-abelian Hodge theory. And in the very end, I'm going to show a novel and curious connection to computer vision that I recently discovered. Okay, but what is the plan? Well, the plan is to begin with, I want to answer the question, what is a degeneration? So I actually want to answer what that is. In the second part, I'm going to talk about Bruhat-Tits buildings and convex hulls. So we've already seen something about buildings, but these are a little bit of different buildings because here we're in the affine building setting. And this is what we're going to talk about in the second part. In the third part, I'm going to give these classification results on Mustafin degenerations. In the fourth part, we're going to be concerned with this application in non-abelian Hodge theory and p-adic non-abelian Hodge theory. And in the very last part, quickly going to talk about this application in computer vision, this funny application in computer vision. Okay, so what is a degeneration? I want to illustrate this in a very easy example. So we have a curve, the curve given by x times y minus 1 is equal to 0. So it's a real affine curve. And as an object in algebraic geometry, it has some interesting geometric structure. And one of the data we may look for is the degree of the curve. And the degree is, of course, the maximal number of intersection points with a line. And this line I didn't draw by accident, namely this line maximizes this number. So the degree of this curve is equal to 2. Now, what these degenerations now do is they transform this green curve, this x times y minus 1 equal to 0, they transform it into a new object in a sort of limiting process, such that the limit of this limiting process is now a combinatorial object and carries this degree being equal to 2 as a combinatorial datum. So what these degenerations do in some sense, they transform geometric data into combinatorial data in some sort of limiting process. And how do we do this in this case? Well, in this case, we can simply replace the 1 by a parameter t. For t equal to 1, we get the curve back that we started with. And now we let t go to 0. And when we let t go to 0, this curve gets closer and closer to the coordinate axis. And in the limit, we get the union of the two coordinate axes. So we get the x-axis and the y-axis. But this, this limit is a curve, but it's also a combinatorial object because it's a line arrangement in the plane. And what is the degree of a line arrangement in the plane? Well, the degree was the maximum number of intersection points with the line. Now, two lines in the plane intersect at most at one point, so two different lines, of course. We can't allow the blue line to be the same as the green lines in this curve, but so two different lines intersect in at most one point, and in this case, the degree is simply 2, because for every line in the line arrangement in the plane, we will get one intersection point in the generic case, and so the degree being equal to 2 is really a combinatorial datum here, because it's simply the number of lines in the line arrangement in the plane. And this is exactly what these degenerations achieve. They achieve transforming geometric data into combinatorial data. A little more formally, a limiting process of a variety x with limit x0 that preserves geometric information is called a degeneration from x to x0. So here we have a schematic picture of this. We have a parameter t that sort of runs from t0 to 0. For t equal to t0, we get the variety x back that we started with. For every value of t in between, we get a different geometric object, for example, xt tilde. When we let t go to 0, we really get this limit x0, this variety in the limit x0. That on the first sight might look completely different than the variety x that we started with, but it still carries the relevant geometric information, the geometric information that we are interested in. And so what these Mustafin degenerations do, they ensure us that this x0 is going to be accessible by combinatorics. Now, for the experts in the audience, for us, the degeneration is always going to be a flat and proper scheme over a discrete valuation ring. Then x is going to be the generic fiber, and x0 is going to be the special fiber, and t is, of course, going to be the uniformizer. And so letting t go to 0 then corresponds to modding out t, so modding out the uniformizer in the defining ideal, because actually all degenerations that we look at today are also going to be projective. Okay. Now, this is, of course, a very powerful technique, and a central question in algebraic and arithmetic geometry is the existence and construction of degenerations with given properties. Mustafin degenerations allow a very specific approach to constructing degenerations with given properties. So I quickly have to drink something. And so the approach may be boiled down into 4 steps. The first step is we embed the variety x of interest into an appropriate ambient space y. So this looks like this. So we have a higher dimensional variety y, and we embed x into y. And this y should have the property that the degenerations of y should be easier to understand than the degenerations of x. And therefore, in the second step, we first study the degenerations of y before we understand the degenerations of x. So we have this higher dimensional thing here, and we look at degenerations of this higher dimensional variety. And for example, we may classify what possible limits can occur in these degenerations. And in the third step, one observes that any degeneration of y induces a degeneration of x. So this is what this looks like. So we have this parameter t here. For every value of the parameter t, once again, we get a degeneration of y and of x simultaneously by restricting the degeneration of y in some sense to a degeneration of x. And then this limit of x will live in the limit of y. And then the last step, and that is going to be the hard part, is the relevant geometry and combinatorics of the limit of x, of the limits of x, may be inferred from the geometry and combinatorics of y0. Now, of course, the magic in this approach is sort of like choosing this appropriate ambient space y. And for us, this y is always going to be the projective space, and x is going to be a projective variety. So just because I don't know what the audience is, the projective space associated to a vector space is simply the set of all lines through the origin in that vector space. Okay, so I hope everybody has an understanding of what a degeneration is, or at least an idea what these degenerations are supposed to do. And I would like to come to the notion of Bruhat-Tits buildings and convex halves. So Mustafin degenerations are degenerations induced by combinatorial data in a Bruhat-Tits building. And these Bruhat-Tits buildings, they are central in the theory of algebraic groups, or more precisely in the geometric representation theory of reductive groups. So today we're going to focus on a very specific building. So I think from a Bruhat-Tits building theorist point of view, this is probably the most boring building, but actually for our study, this is going to be a very interesting building, and we're going to focus on the building induced by the general linear group associated to a vector space V, where the vector space is now going to live over a discretely valued field. So I really quickly want to say what a discretely valued field is, in case someone in the audience has never heard about that. And I just want to give a very vague idea of what that is. So the feature of a valued field is that one of the many features is that one may associate a coefficient field small k. So we have this discretely valued field big K, and one may associate a coefficient field small k, and this coefficient field is called the residue field. So I illustrated this here. So we have this field big K, and if it's discretely valued in a canonical form, in a canonical way, we may associate a residue field small k. And I quickly want to illustrate this in two examples. So, and the examples are going to be more of a semantic manner than actually examples in a concise mathematical way. So, so here we have the field of formal Laurent series with rational coefficients. So we have this field big K, which is given, so set theoretically is the sum over all a and t to the n, where the an live in the rational numbers. And these are power series that have only finitely many negative exponents. So these power series, they start somewhere and they start at an integer. So they may have negative exponents, but only finitely negative exponents. And this field of formal Laurent series with rational coefficients is indeed a discretely valued field. And one may associate a coefficient field. And as I said, by semantic argument, in some sense, the coefficient field is, of course, going to be the rational numbers, because we can choose the coefficients in this series expansion, in this expansion of these elements in the rational numbers. Maybe a more interesting example is the field of the p-adic numbers for prime p. So what is this field of the p-adic numbers? Well, it's an analytic closure. It's the analytic completion of the rational numbers with respect to the p-adic norm. So very similar as to how you get the real numbers from the rational numbers with respect to the Euclidean norm. For every prime p, you get a p-adic absolute value on the rational numbers. You take the analytic completion, and then you get the p-adic numbers. And these p-adic numbers have a very cool structure. So one cool feature that they have is that every element in the p-adic numbers also admits a series expansion. And very similar to the case of the formal Laurent series with rational coefficients, we have a series expansion that starts somewhere. It starts at some integer. So we have finitely many negative exponents. But now this series expansion is in p, not in some variable t, but in the prime p. And so we have finitely many negative exponents of p, and for the series expansion to be unique, we may choose these an in 0 to p minus 1. And this already tells us if we can only choose the coefficients in 0 to p minus 1, once again by a semantic argument, that the coefficient field of the p-adic numbers is going to be the field with p elements. So this sort of illustrates what these valued fields, what these discretely valued fields do in the algebraic geometry setting. And I will say this later on again, but essentially what we have here is an algebraic interface between the algebra in characteristic 0 and the continuous algebra, and the algebra in characteristic p and the discrete algebra. So here we really have a discrete field and a field of positive characteristic, and here we have a characteristic 0 field that is continuous because it's really analytically close. And they sort of fit in the same algebraic framework, and that is exactly the feature of discretely valued fields. Okay, so we will use these discretely valued fields in our definition of the Bruhat-Tits building. Of course, I can't give the entire definition of the Bruhat-Tits building because we've seen earlier in the last talk how complicated these buildings can be in general, but I can give you a definition in spirit. So we have a vector space V over a discretely valued field K of dimension D, and the Bruhat-Tits building BD, induced by the general linear group of this vector space, is the geometric realization of a simplicial complex. So this GLV induces a simplicial complex. That simplicial complex is going to be of dimension d minus 1. And the vertex set, so while the simplicial complex is a little difficult to explain, the vertex set is easily given as an because it's simply a set of equivalence classes of invertible matrices, and it's exactly the equivalence classes of GLV mod the SLV group. Yes. So because I can't give you a formal definition, I'd rather show you a picture. So this is a local realization of the building B2 over the two adic numbers. And so how does this building look? Well, you have a vertex in the middle. And let's say this vertex corresponds to the identity matrix. And then you have three edges, then you have two edges, two edges, two edges, and so on and so forth. And you do this infinitely often. And what you get is this building B2 over the two adic numbers is some sort of fractal tree. So this is an infinite dimension, sorry, this is an infinite simplicial complex of dimension 1. So we only have vertices in lines. And this is really this nice combinatorial structure that these affine buildings, these Bruhat-Tits buildings associated with the general linear group carry. But of course, here we chose very small parameters. So for example, if we just move to the building B3, so we go up in dimension by 1, we no longer only have vertices and lines, but we also have triangles. And then we successively glue triangles to each other. And in some sense, these buildings can get arbitrarily complicated for more complicated parameters, but they will always remain cut zero spaces, if that means anything to you. Now, a very important notion for the theory of Mustafin degenerations is the notion of a point configuration. Now, a point configuration is simply a finite set of vertices in the Bruhat-Tits building BD. So here we have an example. So here we really only have these three vertices, this red one, this purple one, and this orange one. And this is a point configuration. Now, the interesting feature of these point configurations is that so very similar to how you do this in R to the n, you may associate a convex hull which mimics the notion of a polytope in R to the n. So in R to the n, we quickly recall this. We have a finite set of points in R to the n, and if you take the convex hull, we get a polytope. And this polytope is defined in some sense by the feature that if you take 2 points in the polytope, the line between these 2 points will once again lie in the polytope. So the shortest path, or in other words, the geodesic. And that is exactly what you can do here as well. And actually, you can be even more sophisticated, which is actually the notion that you use for Mustafin degenerations. But for now, you can simply think of taking geodesics in this Bruhat-Tits building, and therefore the convex hull of these 3 points is simply going to be this green part. So we really take the minimal set that contains these 3 points that also contains the geodesics between any 2 points in that set. So this is simply going to be this finite structure, and this is indeed a finite simplicial complex. And as I said before, for these Mustafin degenerations, you do something that is slightly more complicated than that. It's a little finer, but essentially this is the way you can think about when you can think about these convex hulls. Now we have chosen very small parameters, once again in this picture, as I mentioned before, and we could just be lucky. So of course, the convex hull of any finite number of points with this geodesic definition is going to be a finite simplicial complex. But if we go up in dimension, this might get more complicated. But thanks to the theorem of Faltings, this is not true. So Faltings proved in 2001 that for any point configuration gamma, we have indeed that this convex hull is a finite simplicial complex. And in fact, Josvik, Stumpfels, and Yu strengthened that result in a very combinatorial study, where they proved that this convex hull is in fact a tropical convex hull of finitely many points. And this means that these convex hulls may actually be computed in something that is called a valuated matroid. So you don't have to know what that is, but what's interesting about this theorem by Josvik, Stumpfels, and Yu is that they actually give an algorithm how to compute these convex hulls in these Bruhat-Tits buildings, and they actually taught it the computer. So if you're interested in computing these convex hulls, there is a polymake package that has since been improved 2 years ago by Leon Zhang, who really sped that up. And convex hulls in this Bruhat-Tits building BD can now be computed very, very fast. And so in a few slides, so some slides later, we will actually see an example of this output. So how these convex hulls look and what these implementations can do nowadays. Okay, but now I said everything I wanted to say essentially about Bruhat-Tits buildings and convex hulls, and now I want to come to the classification of Mustafin degenerations. So in general, the definition of Mustafin degenerations is quite complicated. So I will give you one definition in spirit and one motivation, and then I hope you're sufficiently motivated to read up on the formal definition after the talk. But this should really illustrate what these Mustafin degenerations actually do. So what they do, while the definition, the formal definition, it's not super clear what they do actually. Okay, so what is a Mustafin degeneration? Well, a Mustafin degeneration is a degeneration of an embedded projective variety. So it really depends on the embedding. And we have a projective variety X that lives in P of V, induced by a point configuration in the Bruhat-Tits building associated to V. So the interesting part here is that this X is going to live over big K. So this is going to live over the discretely valued field big K. But the limit of the Mustafin degeneration is going to live over the residue field small k, so over this coefficient field. Now let's say we have the big K be equal to the p-adic numbers. Well then, this X is going to live over a field of characteristic 0 that is in some sense continuous. So we consider an algebra geometric object in characteristic 0, and the limit of this degeneration is going to be an algebra geometric object in characteristic P, because it lives over the field with P elements, Fp, and it's also in some sense going to be a discrete structure, because of course Pf, the projective space associated to Fp to the n only has finitely many points. So, and what these Mustafin degenerations therefore do in some sense is they are a combinatorial dictionary between the algebraic geometry in characteristic 0 and the arithmetic geometry in characteristic P. Now, in some sense, they're a formalization of the following idea, and this is the motivation that I wanted to give. So let's say you have a bunch of invertible matrices that live over Qt. This is a d by d, so every gi of t is a d by d matrix that depends on the parameter t. And for any value of t, we indeed obtain a map from pq to the d minus 1 to pq to the d minus 1 to the n, where the map to the ith factor is simply a linear map that depends on, so that is given by gi valuated at the value of t. And for almost all t, we are going to have that ft is indeed an embedding, and that is simply because the determinant being non-equal to 0 is an open condition. So for a risky dense set in Q, ft is going to be an embedding. And what these Mustafin degenerations do, in some sense, they distinguish between taking the limit of the map and taking the limit of the image of the closure, sorry, of the closure of the image of that map. So we define the ideal IT as the ideal cutting out the closure of the image of this map ft. And then we let t go to 0 for the map. So we can, of course, because these are simply matrices, depending on the parameter t, we can clear the denominators. This will not change the map. This will not change the maps ft. So we can simply take the limit t to 0 in these maps. So in these maps git. But on the other hand, we can also, in some sense, take the limit of this ideal it for t to 0. And then what one will see is that the closure of the image of this map is simply going to live in the vanishing set of the limit of the ideal. But in general, these things are not equal. These things are only equal when the limit of all these gi are also going to be invertible over the rational numbers. But in general, the limit, so the closure of the image of the limit of the map is going to be contained in the limit of the closure of the image. And so this, in some sense, defines the Mustafin degeneration of the projective space. So the limit of the Mustafin degeneration of this projective space induced by this gamma. So gamma was the point configuration because it's a set of invertible matrices. In some sense, it's going to be a set of equivalence classes of invertible matrices. This is exactly this gamma. This is the point configuration. And the limit of the Mustafin degeneration of the projective space induced by this point configuration is going to be the vanishing set of the limit of the ideal defined in this manner. So let's do this in an example. So now we have as a base field the field of Hahn-Milnor series with rational coefficients, and gamma is the point configuration given by these three invertible matrices over this field. Then what we see is if we let t go to 0, so if we do this, then we're going to get that G1 is equal to G2 is equal to G3. Namely, they are all going to be the matrix where we have all zeros except for the entry in the bottom right. Therefore, the closure of the image of this map is simply going to be a point times a point times a point. On the other hand, the limit of the Mustafin degeneration of the projective space in the projective space over Q to the 2 to the 3 is the union of 3 P2s and 3 P1s times P1s. So here we really see a difference. So and the computation of this is of course done in the computer algebra systems. I didn't show you how to actually do this, but this really illustrates that if we simply take the limit of the map, we only get a point in this product of projective spaces. But if we take the limit in terms of this notion, in terms of this framework of Mustafin degenerations, we actually get something of the correct dimension. So we actually here get a P2 times a P2 union with a P2 union with a P2, and then once again 3 copies of P1 times P1. Okay, so maybe 2 more examples that are more combinatorially flavored. Here we have the base field, the p-adic numbers, and the vector space is going to be the p-adic number squared, and X is the associated projective space. And let the point configuration be given by 2 points that have the property that they are connected by an edge in the Bruhat-Tits building. then the limit of the Mustafin degeneration of the projective space induced by this point configuration is the union of two projective spaces over the finite field, so over the field fp squared. So it's the copy. So it's like two copies of the same projective space, and they will indeed intersect in a single point. Let's do another example. So here we have the base field again, the field of formula Roth series with rational coefficients. And as a vector space, we have k to the 4, and x is the projective space. And let gamma be given as 3 points. So here's an image that you can compute nowadays with polymake. So gamma is a point configuration such that the three vertices here, so this vertex, and this vertex is gamma, and they should have the property that their convex hull looks like this. Then the limit of the Mustafin degeneration of the projective space induced by gamma, induced by this point configuration given by this discrete data, has 4 irreducible components. So we already saw in the last example that the number of irreducible components was the same as the number of irreducible components in this convex hull. And here we once again see the same thing. So the number of irreducible components in this limit of the Mustafin degeneration of the projective space is again 4, is again the number of vertices in this convex hull. And one can do even more. So this convex hull here, this induces in some sense a subdivision of a simplex. And every maximal cell of the subdivision, so we see this on the right-hand side here, is a polytope. And every such polytope will correspond to canonically to one of the irreducible components in the limit of this Mustafin degeneration. And indeed, it's even more. So for the expert, the irreducible component, the variety of the limit of the Mustafin degeneration corresponding to any such polytope is exactly the toric variety induced by the polytope. So here we really have a toric degeneration of these Mustafin degenerations. Okay, this is really the kind of combinatorial structure we expect in these limits of Mustafin degenerations, and this is a very beautiful combinatorial structure, I think. And a central question in the theory of Mustafin degenerations is the classification of all limits of a given variety. In the literature, there's a big focus on Mustafin degenerations of the projective space. And I've already sort of told you the idea how to go about in such a classification effort. Namely, this point configuration gamma, on the one hand, induces this convex hull, convex of gamma. And on the other hand, it also induces the Mustafin degeneration of the given projective variety. And of course, the idea is that this convex hull should know something about the Mustafin degeneration of the projective variety. And this was already observed by Mustafin in his original work. Namely, what he observed was that if we once again look at the Mustafin degeneration of a projective space, then and let gamma be a point configuration, x0 the limit of the induced Mustafin degeneration, then the dual intersection complex of the limit of the Mustafin degeneration is determined by convex of gamma. So what this means is that the number of irreducible components of this limit and their intersection behavior, so the dimension in which these irreducible components intersect, is completely determined by this simplicial complex structure convex of gamma. So indeed, this convex of gamma knows everything about the combinatorial structure of Mustafin degenerations of projective spaces. Now, of course, this is an object in algebraic geometry, and one would also like to have a complete geometric classification. And this is something that I did in a joint work with Bing-Ning Li. Namely, what we showed was that the geometry of this limit is also completely determined by this convex hull. So indeed, these convex hulls give us a complete classification of the Mustafin degenerations of projective spaces. And so how we prove this is we take this interpretation of this convex hull as a tropical convex hull, and then we study this tropical convex hull in terms of something which is called tropical intersection theory, which is a combinatorial analog of classical intersection theory in algebraic geometry. And this allows us to explicitly construct the limit directly from this convex hull, convex of gamma. And actually, our work also enables a linear algebra algorithm to compute the limits of these Mustafin degenerations. Okay, so now we have a complete understanding. So since 2007, we have a complete understanding of the Mustafin degenerations of projective spaces in the literature. And of course, the question is, what about other varieties X? We remember the strategy that we chose in the beginning. So the idea was to first embed the variety X of interest into an appropriate ambient space Y. Then we've done X, we have embedded X into the projective space. Then we wanted to study the degenerations of the ambient space Y. We've done that. We've classified the Mustafin degeneration of the projective space. And then any degeneration of the ambient space should induce a degeneration of the subvariety X. That is indeed true almost by definition. And in the end, so the hard part, that is what I promised in the beginning, is that the relevant geometry and combinatorics of the limits of the embedded variety X may be inferred from the geometry and combinatorics of the limits of the ambient space. And this is something that I did in a joint work with Annette Werner. Namely, what we proved is, so if we have a smooth and projective curve living over the p-adic numbers, then we may embed that in pk to the 3 or pk to the 4. So indeed, we get all smooth and projective curves for the p-adics because any such curve may be embedded in pk to the 4. And what we show is that for almost all point configurations gamma, the dual intersection complex of the limit x0 is given by gamma. So this gamma determines already the complete combinatorial structure of the Mustafin degenerations of the curve. Very similar to the theorem that Mustafin and Faltings and Cartwright-Helbig-Stumpf-Werner proved that I mentioned earlier. And we also formulate a conjecture on how this should work for surfaces and higher dimensional varieties. And the idea is sort of that this gamma is in some sense the zero-dimensional part of this convex hull, convex of gamma. And therefore, so for the one-dimensional curves, the zero-dimensional part should tell us what's going on. So if we go up one dimension, then for surfaces, the one-dimensional part of the convex hull should tell us what the combinatory structure is, and so on and so forth. But this is still an open problem. What we do indeed get here a combinatorial classification of a large family of Mustafin degenerations of all smooth projective curves over the p-adics, where I should say that we have to take p sufficiently large, and also this condition on p being sufficiently large, but also the bound on the ambient space and the embedding, so that we can only embed the curve into pk to the 4 at max. That really comes from the fact that we heavily use computer algebra in our proof. And so for the higher dimensional cases and also for the special cases of the primes, the computations just don't finish. And so we don't know yet. So that is the current state of affairs when it comes to the classification of Mustafin degenerations. And now I slightly want to change topics and then sort of come back to Mustafin degenerations, because now I want to talk about a p-adic Narasimhan-Seshadri theorem. Or maybe this is a good place. So if there are any questions, this may be a good place to ask questions now. Oh, okay. Guess everything's clear. Perfect. Then we can go to this next chapter, a p-adic Narasimhan-Seshadri theorem. So what is this about? This potential theorem that I'm going to talk about in a few seconds. Well, it's about vector bundles, and vector bundles are fundamental objects in algebraic geometry. And so if you've never heard about vector bundles, this is one way of thinking about it. This is a very schematic way of thinking about it. So we fix an algebraic curve x and a positive integer d. And to every point x on this algebraic curve, we associate a vector space Vx of dimension d, such that for near points on this algebraic curve, the vector spaces Vx and Vy are similar. And this construction is then called a vector bundle of rank d. So what we do here, so this black thing is supposed to be the algebraic curve, the same here. And here we have a vector bundle of rank 1 on these curves, respectively. So we simply associate a line to every point on the curve. And so for these, so if we look at these pictures, so if we move along these curves, then what we see is that this line actually in some sense moves also with this curve. So this can be seen here, but maybe is clearer in the case of the circle. So to every point we associate a tangent line. Then if we move along the circle, then actually this tangent line smoothly follows this movement. And this is exactly this condition that for near points the vector spaces are supposed to be similar. Okay, so a big focus in the literature is on so-called stable vector bundles and semi-stable vector bundles. And this is a condition on the so-called slope of the vector bundle. This is just a numerical condition. And this focus on these semi-stable and stable vector bundles is especially accentuated in the classical Narasimhan-Seshadri theorem. This is a very strong theorem that connects the theory of vector bundles with one of the fundamental invariants of algebraic curves, namely the fundamental group. So it's already in the name how fundamental this invariant is. And it states the following. So let x be a smooth projective curve over the complex numbers. And I should say the complex numbers are not a discretely valued field. Then there is a correspondence between the stable vector bundles on this curve and certain representations of the fundamental group of x. And we actually know what these representations are. It's just a technical condition that I didn't want to write down. So what this theorem tells us is that on one hand, we have this algebra geometric world of stable vector bundles. And on the other hand, we have this group theoretic world of representations of the fundamental group. And this theorem tells us that these worlds are in some sense the same world. This is, of course, a very, very strong theorem. It's since been generalized in the famous Simpson correspondence. So this has been extended to all representations in some sense. And then on the algebra geometric world, we have the Higgs bundles. Yeah, this will not play a role. I just wanted to mention that there has been a lot of work in generalizing this theorem to other classes of vector bundles and so on and so forth. But one condition that is sort of weird in this theorem is that we have this condition that x has to live over the complex numbers. So a big question is whether this theorem can be extended to other fields that occur in arithmetic geometry. And in particular focuses the question, is there a p-adic analog? So this question is of particular interest. And this is still an open problem, but an important first step was done by Falkings in 2005, who proved the following. So let x be a smooth and projective p-adic curve. Then one direction of a p-adic analog holds. So every representation of the étale fundamental group, so we have to move to the étale fundamental group for some technical reasons, induce a semi-stable vector bundle on this curve x of degree 0. So the stable vector bundles are replaced by the semi-stable vector bundles of degree 0. But other than that, this is the exact same theorem, but it's only one direction of this theorem. And the big question is, of course, if the other direction also holds. So this is, and I want to stress this again, this is still an open problem. So in other words, so one can also phrase this in, is every vector bundle, this is every semi-stable vector bundle of degree 0 reached. So here a semi-stable is missing. So the question is every vector bundle in this set, is every semi-stable vector bundle of degree 0 on this curve reached for every curve? And the answer is indeed yes for vector bundles of rank 1, but even in rank 2. So even when the dimension of all vector spaces is only 2, this question is completely open. And one important theorem that gives an indication on how to possibly prove that every vector bundle of higher rank is also reached is the following by Deninger and Werner from 2005, who proved a vector bundle on such a curve is reached if there exists a degeneration of this vector bundle on the curve, so a simultaneous degeneration with a special limit. And so this is called the Deninger-Werner criterion, and this is really a degenerative criterion on whether a vector bundle is reached by Falting's construction. And so then, of course, a p-adic Narasimhan-Seshadri theorem would be proved if one could show that every semi-stable vector bundle of degree 0 on a smooth projective p-adic curve admits a degeneration such as Deninger and Werner prescribe. So for the experts, I should also once again say what this criterion is. So it means that the curve admits, so the vector bundle on the curve admits strongly semi-stable reduction. So after finite pullback of the curve, under finite smooth pullback is what I should say, there exists a degeneration such that the special fiber is strongly semi-stable on every irreducible component. So what did Deninger and Werner prove in some sense? Let me show it once again in the picture. They prove that there exists a subset here of these semi-stable vector bundles on x of degree 0, such that the arrow goes in the other direction. And of course, a p-adic Narasimhan-Seshadri theorem would follow if we could show equality here. Now the goal is in the literature to show that every semi-stable vector bundle of degree 0 satisfies the Deninger-Werner criterion. Now, there's been a lot of work. I quickly want to mention an approach that was developed by Annette Werner, so the Werner and Deninger and Werner and myself recently. And so it uses the following fact. So for a p-adic Narasimhan-Seshadri theorem, it would be enough to verify the Deninger-Werner criterion for syzygy bundles. So this is, in some sense, a kernel. So syzygy bundles are defined as via a short exact sequence. So we have here the structure sheaf of the curve that we enter. So sorry, this is really bad notation. I just realized I probably should have called this x and this also x. So the C is supposed to be x. This is supposed to be the smooth p-adic projective curve. And so we have this map here. So given by n sections, and then the syzygy bundle. These syzygy bundles, they are simply the kernels of these maps. And this is how you define these syzygy bundles. And what's cool about these bundles is that these bundles allow the use of combinatorics and computer algebra. And our ansatz was to use our combinatorial classification of Mustafin degenerates of curves to constructively verify the Deninger-Werner criterion for all relevant syzygy bundles. So we haven't quite achieved that. But what we could show is that, okay, so this technical conditions, because our computations wouldn't end, but for every smooth projective p-adic curve x, we construct an infinite family of syzygy bundles of any rank that admit the Deninger-Werner criterion. So for every rank, we have an infinite family of syzygy bundles that are reached by Falting's construction. So in other words, what we showed is that this set here, this set is really big. So we don't quite know if it's equal, but this set is really big. And there is actual hope that these sets can be equal. And this result also allowed us to solve an open problem that was posed by Holger Brenner in 2005. Namely, Holger proposed a possible counterexample for the question if every semi-stable vector bundle of degree 0 satisfies the Deninger-Werner criterion. So in other words, what he showed is, so we have a syzygy bundle that is defined in very easy terms on the Fermat curve. And so it's simply given by the kernel of the map, where this map is actually defined globally by x squared, y squared, and z squared. So if this doesn't mean anything to you, it's not too bad. All I'm trying to say is that this is a really easy and explicit example, and he proved that the obvious degeneration of this very easy and explicit example does not satisfy the Deninger-Werner criterion. This was actually an open question for quite some time, if this is actually a counterexample. So Holger said essentially, so there is a semi-stable vector bundle on the Fermat curve for degree 0, and I have some reason, because it does not set, so because for infinitely many D, the obvious degeneration does not satisfy the Dehninger-Werner criterion. I have good reasons essentially that this element in here could not lie in here. And the question whether this was actually a counterexample was, as I said, quite an open question for quite a long time, despite its very explicit nature. And this shows how difficult this problem actually is, in my opinion. Now, we could show that Brenner's example is indeed part of our constructed family and therefore not a counterexample. And actually, Brenner's example was the original motivation for our work in 2019. So we started out trying to rule out this as a counterexample, and then realized that we can construct this pretty large family. So I think I have like 5 more minutes, right?
Yeah.
Yes. Okay, perfect. Okay, good. So I try to be fast, but also understandable. It also doesn't matter if I don't come through.
No, well, I mean, if it's a couple of minutes more, it's also not a problem.
Okay, thanks. Okay, so now I want to come to this application in computer vision, and I found this a very, very funny and very interesting application. And so we're now in a very specific part of computer vision, namely multi-view geometry. And in multi-view geometry, one considers a very specific computer vision problem, namely, what are the properties of a real-world scene given several images of it? So here I borrowed a picture from the internet, which sort of illustrates what I'm trying to say here. So here we have a 3D object, and then we have a bunch of cameras. So in this case, now here we have 3 cameras, and then we simultaneously take pictures of this 3D object with all cameras. And then the question is, what can we say about this 3D object from the pictures that we taken? So can we sort of reconstruct this 3D object in the real world from these pictures, and so on and so forth? And this may actually be modeled in algebraic geometry language. So this is the way these computer vision people work, and I should also say they actually work with a projective space, because they want to remember in their construction that if you have 2 parallel lines, that they actually look as if they're getting closer when you look from a perspective. So this is actually the setting that computer vision people work with. So what they do is, so let's say we have n cameras, and then for n images, the question is modeled as follows. So for every camera I, so we number them by 1 to n, every camera I corresponds to a projection from 3 space to 2 space. I mean, this is essentially what a camera does. We simply have a projection from 3 space to 2 space, and this is usually a linear projection. And so therefore, this projection from 3 space to 2 space is modeled by a matrix of size 3 by 4 of rank 3, and a map from P3 to P2. And this is a rational map. And then one collects all these matrices A1 to AN in a tuple, and one associates this map F underline A from P3 to P2 to the N is once again a rational map, which is given by the map AI in the ith factor. So the map to the ith factor of P to the N is given by AI. And then the closure of the image of this map is called the associated multi-view variety. And this is actually a very powerful object in computer vision. So you can ask a lot of reconstruction theorems in this. So you can ask a lot of reconstruction problems in this language, and you can also answer a lot of reconstruction problems in this language, in the language of this multi-view variety setting. Now, there's a very beautiful theorem from an algebra geometric perspective by Ahold, Sturmfeld, and Thomas from 2013. And so what they showed is that the space of multi-view varieties, so we simply look at the set of all multi-view varieties, they may be embedded into the corresponding Hilbert scheme, because all these multi-view varieties in the generic setting at least have the same Hilbert scheme. But the space of these multi-view, they all have the same Hilbert function, and the space of these multi-view varieties, it lies dense in an irreducible component of the respective Hilbert scheme. So in other words, what they showed, so we associate the Hilbert scheme to the Hilbert function that corresponds to all of those multi-view varieties, and then there is a single distinguished component such that all these so all the points corresponding to these multi-view varieties lie in here, so lie in this in this distinguished irreducible component, and if we take the closure, we actually get the entire irreducible component of this Hilbert scheme. So we, in some sense, really have a computer vision interpretation of at least one of the irreducible components of this Hilbert scheme. So I don't, yeah, okay, so it's known that there are also other components. I think my AirPods just stopped working.
We hear you fine, but it seems indeed that you don't hear. Okay, let's see if we can manage to.
Oh, sorry, can you hear me now?
Yes, now it's back. Thank you.
Okay, sorry. Yeah, okay. Okay. Okay, as I said, what this theorem says is that there's one distinguished irreducible component of the Hilbert scheme for which we have a computer vision interpretation. There are several other irreducible components of the Hilbert scheme, but this one really has a computer vision interpretation. But what is not known is what this boundary is of this irreducible component. So this is an open question, and this is something that I thought about last year. So what does the boundary of this one irreducible component look like? What other varieties do I get if I take the closure in this irreducible component? And the starting point is the following theorem by Anna from 2005, who proved that one may compactify the Bruhat-Tits building BD by full rank matrices of size E times D for E smaller or equal than D. So what she showed in some senses, I mean, I explained earlier, this building is built out of, so we have this vertex in the middle with 3 edges, and then we have 2 edges, 2 edges, 2 edges, and so on and so forth. And we do this infinitely often, and we may compactify this building by, in some sense, taking, so at like if we take the limit along each path, we in some sense put a matrix of lower size or of smaller size at the end of each path. And then you can do this successively, and then you obtain a Bruhat-Tits building. So then you obtain a compactification of the Bruhat-Tits building by matrices of lower size. And the observation is that if you take a point configuration in the boundary of the building, in the boundary of the compactification of B4, this indeed induces a degeneration of multi-view varieties that we call generalized Mustafin degeneration. And indeed, the limit of these degenerations of multi-view varieties lie in the boundary of the irreducible component of the Hilbert scheme that we looked at. And the hope is that the entire boundary is reached by this construction. And then I proved a structure theorem on what kinds of limits one can get, but I don't think this is so interesting that I should go any more over time as I've already done. So thanks a lot for your attention. I'm very happy to answer any questions that occur.